Good afternoon, this is Schweitzer, and we are going to be doing a little video here on ionic properties. In this situation, there are three main properties. We will be discussing bulk crystals and melting points in this particular video, and I'll break this one off into a separate video to shorten it up some. Alright, so first things first is, this is what's called a bulk crystal, commonly known as a pile. So, how would someone give this thing a name? It's like, this is kind of where we're coming down to it. If you break it in half, the left side's the same as the right. A common example of this little bulk crystal would be if you look at a small little chunk of table salt. They look like these little cubes. That's because when they break along these lines and form those little cubes. So again, the name of how would you give a name of this thing? Well, it turns out that it's kind of difficult because there's billions and billions and billions of these. So it turns out they give what's in this situation that they didn't have to. It's just how they did it. They just gave the name of the cation. Maybe that's the cation that we don't really know. And they gave the name of the anion, name of the cation, name of the anion. And I don't really know why. Maybe a long time ago they couldn't figure out how many were there, or they couldn't figure the ratio out between the two. This looks like 1 to 1, but it could be 1 to 2 or 1 to 3. So that's just how they did it, and that never, ever, ever did they give quantities, even though there were some ratio there. Formula. They're going to give you what's called the empirical formula. Maybe this came later after they figured it out, but it's the simplest ratio. Empirical formula is the simplest ratio. Now we talked about this a little bit with like calcium oxide, +2, -2, which means you got calcium oxide, not calcium 2 oxide 2. Keep in mind, if you understand how this bulk crystal works, you'd realize it's just a great big pile. And the positives attract the negatives because they're oppositely charged. And there's not a little package of 4 of these that's unique to everything else. No, it's really just a big pile of cations and anions. So we always put it in the simplest ratio just to show that that's just the ratio of the entire crystal. Again, we just summarize that, why they're listed as empirical. Okay. Alright, bulk crystal. Fill in your definition of empirical formula, simplest ratio. Again, this is our first property of ionic compounds. This is not a molecule. Alright, molecule, like let's say water, has single bonds and double bonds. Okay. It's very strong because it's very interconnected. When you melt an ionic bond, what breaks? Okay, an ionic bond breaks. Make sure you note that. When we melt this thing, we're shaking these things, and we just shake, and it breaks off, and then we break that ionic bond. Because it's so strong, it's likely a solid at room temperature, or any other temperature really on Earth. There's a couple of them that maybe could be liquids or close liquids at several hundred degrees, but this thing typically have very high melting points that could range from, let's say, 500, even like 3,000 degrees Celsius. Okay, so really quite ranging, but quite high typically. Alright, so again, what breaks when you melt an ionic compound? An ionic bond breaks. May sound redundant, but it's the way, there'll be some other ones that's not as easy as that one. So what controls the melting point of an ionic bond? That's our main topic here in this bulk crystal. Well, it's the charge of the cation, the charge of the anion, this is just Coulomb's law, and the distance between the two, which is we call the so D equal internuclear distance. So this really is the from one nucleus to the other nucleus. That's determined by the size or the radius of the atom, how many energy levels you have. We could have big atoms, lots of energy levels, could have a large distance between them. Or we could have two small atoms that are relatively close between them. Alright, so first thing we consider in our sort of making decisions is the charge. So the force equals the charge of the cation, charge of the ion. That's the first step we'll be looking at. If those charges are the same, then we move to internuclear distance. So what I do is I just look at the charges. What are the charges here? What are the charges here? This one is, if you don't know, and there's a little typo here, I'll fix that. That should be a 3 here, and there should be a 2 here. We got a +3 and a -2, so I'll plug them in here. I got a 3, and I got a 2, and therefore, multiply together, you get 6. That's proportional to that charge. This guy is +1, this guy is -1, and multiply together, you get 1. That's proportional to that guy. So likely this guy is 6 times larger than that, if assuming that it's somewhat similar internuclear distance. That's how that works. Look at charges. So if the melting points, if these are is our first look, and they're the same, then the next thing to look at is the size. So let's look at how these sizes work. I kind of explained them already. Okay, but really, let's get a good idea. Why are they sticking together? Only thing that sticks together is that positives attracting negatives. And of course, positives repel, negatives attract. So I'm going to do the attractive forces here in black. I'll do the repulsive in red, looks like. So attractive, what tracks here? Well, we have an attraction here to its own electron, but it also has attraction to other guys' electrons and other guys' electrons. I get traction here to this guy's electrons. Okay. Remember, closer you are, the lower this is, the more the force ramps up. Alright, how about this guy? This guy needs to attract all the way over here to get to that guy, and all the way over to this guy. That is what's going to allow these guys to really attract. This guy, of course, only got to go this distance. Okay. But the larger the distance is here, the bigger the atoms, the larger the attractive force. The smaller the attractive force. Alright, and then you have your repulsive forces, which of course are electrons repel, and these guys repel. So a nice bond will form when the repulsive forces are, if these are greater than these ones. Alright, so internuclear distances, larger distances equal lower melting points. Of course, this is our second thing that we're going to look at, the distance, which is the size of the atoms. Alright, so let's try this out. How does this work? The first thing you want to do from your decision tree is just simply assign charges. So that's the first thing we're going to look at. So get your ion sheet out or look at your periodic table. You could pause the video now and assign all the charges. Or if you don't know, you can follow along. I'm going to uncrisscross this -2, +3, +3, -1, +1, -1, uncrisscross, +1, -2. Alright, from the lowest melting point is going to be the 1, the lower charges. So this guy is a 1, 1, this guy's a 1, 1. So I got these two first. They're tied. Now I'm going to go to size. Notice we'll always have one of them will be the same. We're going to just compare these two. And that would be the size of the atoms. Larger means lower melting point. Find these two guys on your periodic table. This guy's got 3 energy levels. This guy's got 2. So NaCl is the lowest, followed by NaF. And we start working our way up. As our charges increase, we just simply start taking the next biggest one. This guy is 1 and 2, 1 and 3, 2 and 3. So NaCl A2O is next, followed by aluminum chloride, followed by aluminum oxide. That would be the highest. Check your answers there. Alright, so sample style question here. Last energy, which is the name of the energy in the crystal, is salt. With energy to separate the ions. Which of the following pairs of ions is the energy that is required to separate the ions the largest? Pause it. Try it out. Okay, so we're going with larger ions, so we can get rid of A, get rid of B. Which of these is the largest? Well, they're both the same charge, so I go with the smallest atom here. So the answer is going to be magnesium, because magnesium is smaller than calcium. Thank you very much.